Cool. All right. Hello. How's it going, everybody? Welcome back into the stream today. I hope you're having a wonderful day so far. How's it going, everybody? Welcome in. Welcome back in. I didn't stream yesterday, dude. I was just beat. It's been I released my last product yesterday. For like this current sequence I was doing, I was building 2 products at once, which pretty much no one on my team really does. I kind of do it pretty consistently. Especially like if they're I guess they're kind of easier products, but still, most people just do one at a time. But they threw me 2 at the same time, and they do that quite frequently when I come off the down ends of my difficult product. So I appreciate you guys for being here and saying what's up. So yeah, I was just pretty beat yesterday. I was just gonna celebrate. I took the day off after work. Took no stream yesterday to just kind of relax and lay back. But we're back today, nonetheless. Hey Lee, how's it going, dude? Data structures class today. How'd that go? Let me know. I'm really curious to. If you guys are back in school and you guys are CS majors, let me know how classes are going. I'm super jelly. I wish I was taking those classes with you. I might ask for your notes or maybe your PowerPoint slides or something, so I can look at them to see what they're kind of referencing. That'd be cool. If you're in my Discord and you're a CS major and currently in classes, consider like dropping your notes and stuff in the Discord within the community resources or wherever. I'll maybe make like a CS majors chat, so only people that are CS majors can actually chat in there. So I won't be able to. I guess I can chat, but I can't. I don't know. That'd be kind of funny. But anywho, maybe I'll have to make it like a tag in the Discord that you're a CS major, right? All right. So, cue the Seth Rogen. Whatever. Okay. My college begins in 2 weeks. Anakat, nice, dude. Where are you going to school at? Are you overseas or are you USA? Well, I guess overseas, if you are overseas is the USA. So are you overseas from me? Are we overseas from each other? Or hello, Austin. How's it going, dude? Welcome back in, my guy. What you been studying? How's your studies been going? Appreciate you for coming in again, like you do every day. You're awesome. Austin, are you in the Discord? Leah, I have to take Calc 1 through 3 through, though, which is the only thing I have to grind. Nice, dude. Yeah, we started to take Calc 1 again on this channel. I got about 2 weeks in, and then I stopped doing it, dude. I have such a bad problem with starting projects, getting like fired up about them, and then fall off the wagon, dude. Oh my gosh. It's brutal. I need to keep up on my I need to keep going, you guys. It's so hard, especially when I've got all these other things I want to do on the channel. I got a 9 to 5. Bro, it's brutal out here. It's so, man. Yukon, nice, dude. Probably got a lot of basketball games then. Those are probably pretty fun. I always wonder what it was like to go to like a school that had like a really big sports program or basketball program, or like I went to Utah State, right? We were Division I college in the United States at Utah and at the state of Utah, northern Utah, but it was a fairly small town and a fairly small Division I school relative to some other ones. Probably I'd say like, I don't want to give false info, but probably like honestly like half the size of a typical D1, maybe like 2/3 the size. So a significant chunk reduced down, which is a lot of students by number. Hey Pineapple, what are you doing? Hey, so we're going to be reading Chapter 2 of Introduction to Algorithms, CLRS. CLRS stands for Corman, Laerson, Rivest, and Stein. So that's what they kind of refer to this book as, is the CLRS, because the Introduction to Algorithms is a pretty broad title. But we're going to be reading Chapter 2 today, which is about 20 or so pages. I think we can get through it fairly quickly, as it's kind of more review, going over, asymptotic notation. So if you guys are, getting intro to algorithms and wanting some, actually to, get into this, this would be a great time to pay attention and focus up this stream. I think I can get through it in one night here because it will be a little bit of refresher with some solidification of stuff. So, but I'm excited to get into this, and really, the second time around, we've already went through DSA and Python up to chapter 11, so which was a pretty significant chunk of that book. Except it just started to get really, really dense, really fast, and into kind of some niche data structures I wasn't really using. I kind of got the gist of what I needed up to trees and stuff, what I really needed, the common core ones, and then there was the back half of the book is kind of really dense things like that. So I'm hoping to, I'm going to try to make it a goal, because this is kind of the algorithms Bible for programmers, is to really get through this one and power through it. I want to, and plus going through algorithms a second time around, I think things will be a little easier for us too, hopefully. Anyways. All right. Cool. Let's go ahead and pause the tunes. All right, you guys, I'm going to go ahead and start recording, as I am going to be chopping these up for kind of an audio book watch back you can do on the channel. I'm going to try to chop up lecture 1 or chapter 1 tonight and get that uploaded for you guys. So be on the lookout for that. I'm going to try my best to get that out as soon as possible. So yes, be on the lookout for that. Anywho, let's go ahead and get into this here. Let's start the recording. Is there a 4th edition, Tim? Oh no. Oh, there might be. Well, we might need to get the 4th edition here, rather. I didn't even know there was a 4th edition. We played ourselves. Look at that. There should be a preface regarding the changes to the 4th edition. Acknowledgements. As we said, the changes to the 2nd, 3rd edition, depending on how you look at it. Pseudocode. Rarely taught topics were removed. Reviewed the entire book and rewrote sentences. So just, I think a basic, a full polishing, basically. Okay, sweet. Well, thanks, Tim. Shout out Tim for putting us on the right track here. We are in Introduction to Algorithms, 4th edition. Upgrades, people, upgrades. If you can tell me the name of that movie, that quote is from, you are a pro. You're a pro. Okay, let's start recording. All right, everybody, we are back in Introduction to Algorithms. We're going to be reading Chapter 2 today. We did an upgrade. We found the 4th edition PDF online. I did not know there was a more recent edition from the 3rd, so that is awesome. So we're going to be jumping into Chapter 2 again today, audiobook style, and I'll be reading aloud as we go. You can join me on stream every single day around 7 p.m. PST as I teach myself computer science and programming live. Thank you guys so much for being here, and let's get into Chapter 2. Okay. Dun, 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 dun. Cool intro. Bang that out quick. Let's go. Okay. Let's get into chapter 2. All right, here we go, everybody. Chapter 2, getting started. Let me know if how the audio is. You want me to turn up my mic, turn down my mic? Oh, robots. Tim, you got it right, dude. Monty Python? No, not Monty Python. I think that's what you meant instead of Michael the Python. You mean Monty Python? It was from Robots, that old movie back in the day. Okay, let's get into this. How do you know that, Tim? All right, chapter 2, getting started. I guess I'll just try to zoom in a little bit more for you guys. Try to make it so it's readable for everybody. Let me know if you want it more zoomed in or whatnot. Let's get into this. This chapter will familiarize you with the framework we'll use throughout the book to think about the design and analysis of algorithms. It is self-contained, but it does include several references to material that will be introduced in chapter 3 and 4. It also contains several summations which Appendix A shows how to solve. We'll begin by examining the insertion sort algorithm to solve the sorting problem introduced in chapter 1. We'll specify algorithms using a pseudocode that should be understandable to you if you have done computer programming, hopefully. We'll see why insertion sort correctly sorts and analyze its running time. The analysis introduces a notation that describes how running time increases with the number of items to be sorted. Following a discussion of insertion sort, we'll use a method called divide and conquer to develop a sorting algorithm called merge sort. We'll end with an analysis of merge sort's running time. All right. Insertion sort. Here we go. Our first algorithm of the book. Let's go. Here we go, boys. Milestone reached. Achievement unlocked. Insertion sort. Our first algorithm, insertion sort, involves the sorting problem that introduced in chapter 1. A sequence of n numbers where we have a sub 1 all the way up through a sub n. And we want to output a permutation where we reorder, we have a sub 1 prime all the way to a prime sub n, where the input sequence such as that the a1 prime is less than a2 prime, which is less than all the way, up to a sub n prime. So basically the numbers are sorted in as less than, so in increasing order. The numbers to be sorted are also known as the keys. Although the problem is conceptually about sorting a sequence, the input comes in the form of an array with n elements. When we want to sort numbers, it's often because they are the keys associated with other data, which we will call satellite data. Okay, this is some good information here. So let's get, so we got keys, and we have satellite data. All right. Together, a key and satellite data form a record. Okay, so we are getting a lot of interesting stuff here. Record with keys and satellite data. For example, consider a spreadsheet containing student records with many associated pieces of data such as age, grade point average, and number of courses taken. Any one of these quantities could be a key, but when the spreadsheet sorts, it moves the associated record, the satellite data, with the key. When describing a sorting algorithm, we focus on the keys, but it is important to remember that there usually is associated satellite data. In the book, we'll typically describe algorithms as procedures written in pseudocode that is similar in many respects to C, C++, Java, and Python, or JavaScript. Apologies if we've omitted your favorite programming language. Okay. If you have been introduced to any of these languages, you should have a little trouble understanding algorithms coded in pseudocode. What separates pseudocode from real code is that in pseudocode we employ whatever expressive method is most clear and concise to specify a given algorithm. Sometimes the clearest method is English, so do not be surprised if you come across an English phrase or sentence embedded within a section that looks more like real code. Another difference between pseudocode and real code is that pseudocode often ignores aspects of software engineering, such as data abstraction, modularity, and error handling, in order to convey the essence of the algorithm more concisely. We start with insertion sort. which is an efficient algorithm for sorting a small number of elements. Right? An efficient algorithm for sorting a small number of elements. Okay. Insertion sort works the way you might sort a hand of playing cards. Start with an empty left hand and the cards in a pile on the table. Pick up the first hand in the pile and hold it with your left hand. Then, with your right hand, move one card at a time from the pile and insert it into the correct position in your left hand. As Figure 2.1 illustrates, you find the correct position for a card by comparing it with each of the cards already in your left hand, starting at the right and moving left. As soon as you see a card in your left hand whose value is less than or equal to the card you're holding in your right hand, insert that card you're holding in your right hand just to the right of this card in your left hand. All right, everybody with me? If all the cards in your left hand have values that are greater than the cards in your right hand, then place this card in the leftmost card as the leftmost card in your left hand. At all times, the cards held in your left hand are sorted, and these cards were originally the top cards of the pile on the table. Okay? The pseudocode for insertion sort is given as a procedure insertion sort on the facing page. It takes two parameters, an array A containing the values to be sorted, and the number of elements n of values of sort. The values occupy positions A index 1 through A index of n of the array, which we denote by A sub 1 through n, like A slice 1 through n. When the insertion sort procedure is finished, array slice 1 through n contains the original values but in sorted order. Right, so you have an empty first left hand, and then you have a pile of cards in your right hand, and you start feeding cards into your left hand. So you first feed this 10, then you pick up this 5, and then you pick up this, and then you pick up the 4, so the 4 gets placed there, the 2 gets then placed there. Now you pick up this 7, and you can see, okay, I have to insert the 7 in between the 5 and the 10. So that pushes the rightmost indexes +1, so the 10 would have to gain an index value. So that's the only bad part. And all of these insertions here from the 5, 4, and 2, if these came before this 10, would also cause a propagation, I guess, of index increases, if that's the right word. Okay, sorting ahead, right? Perfect. Let's. I'm gonna snag this guy here. This is a good pick. All right. So here we go. For I equals 2 to n, so you're going to skip the first card because the first card is already sorted. So if the first card is 10 here, then we're going to start, and the next card is 2, 4, and 5, let's say. We're going to start with 2 because we're going to already have 10 in our left hand by default. So the key is equal to a index of I for the index we're on, right? The integer index we're on. We're going to insert a index I into the sorted subarray of a of 1 slice I less than 1, right? Because the current subarray, a sorted subarray of a, right, will have 1 less than I current index count of items, because all the previous items will have been sorted up to that current card that we're on. So we have a second pointer here, j. So while j is greater than 0 and the value that j is indexing over in the array is greater than the key, right, we're going to increase j. Right? we're going to set the value of the index 1 greater than the current one of j to the current value of j and decrease j until there's no more. Okay, interesting. Okay, let's go over this. Hey, Danny, how's it going? Where'd you get this book? I just looked it up online. Hey, Carlos. Yeah, it's in the Discord, but that's the 3rd edition. I'll update and post the 4th edition, the updated one here. Hey, Virtual Code, welcome back in. Hey, Ray313, what's going on, dude? Yeah, we be self-learning. All right, loop variance and correctness of insertion sort. Figure 2.2 shows how this algorithm works for an array A that starts out with a sequence of 5, 2, 4, 6, 1, and 3. The index I indicates the current card being inserted into the hand, right? Index of I is the current card being inserted into the hand. At the beginning of the insertion of the for loop, which is indexed by I, the subarray, a contiguous portion of the array, consists of elements of A, index of 1, all the way up into I less than 1, right? This is just saying that if we're on some, iteration of this for loop, let's say the 3rd or the 4th card that we're going to try to insert and sort into our left hand, right? Well, all the other cards in the left hand, all the 1, 2, and 3 cards are in sorted order. And so we're going to have to now insert, and we're going to loop again, evaluating over each card, finding a place to insert, right? That is A index of 1 through A index I less than 1 constitutes the current sorted hand. And the remaining subarray, A index I plus 1 through n, elements, right, can correspond to the pile of cards that are still on the table. So instead of creating a new array in memory, we are just taking the first index, which in this case they're denoting as 1, but in normal cases it's 0. We're taking the first index. Oh, well, they're looping over the first number because the 0 index, well, no, they're starting at I equals 2. So index of 1 in this code here, because they don't have greater than or equal to 0. They're not evaluating over the 0 index. So that's kind of interesting that they would have this be not 0 indexed but 1 indexed, right? Cool. In fact, elements A index of 1 through I minus 1, so the cards that are in our left hand currently, are the elements originally in positions 1 through I minus 1, but now in sorted order. Exactly, right? It's the first 3 cards we picked up. If we're on the 4th card, it's the first 3 cards we picked up that are now just sorted in our left hand. We state these properties as formally as a loop invariant. Okay, so let's call here as a loop invariant. I'll look up these definitions later here so we don't waste too much time. I'll kind of go back through and fill in these blanks. All right, so here is our example. So we start on the 1, and we first start on the 2 index because the subarray starts on index of 1, which is the first index, which should be index of 0, but whatever. So 5 by itself is already sorted. So if we come across the 2, we're going to pick this up and move it over to our subarray. Now we're going to loop through the subarray until we find a position that evaluates to where this is no longer greater than this value, right? Or the values at the index of j for the subarray. So as you can see, the 2 says okay, the 2 is still less than the 5. We need to push the 5 over, and the 2 will take that place. We'll right. In this place, the 4 comes in. Okay, the 5 is greater than the 4, so the 5 gets saved as an index spot greater than 1 plus, or increased by 1, and the 4 then goes here. We evaluate against the 2. Oh, it's greater than the 2, so we need to just save right here. All right, we're on the 6 now. We evaluate across the 5. Oh, we're actually too big. We can't go any further, so we're just going to stay where we're at. We're going to evaluate across the 1. We evaluate on the 6. Oh, the 6 is bigger than the 1. We push the 6 index plus 1. Oh, we evaluate. So now the 1 is right here where the 6 is, and the 6 is right where the 1 is. Now we have a 1 right here where my cursor is. We evaluate across the 5. Oh, the 5 is greater than the 1. We push the 5 as the index greater. So now we have 6, 5, 1. Now we have evaluating against the 4. The 4 gets pushed. 6, 5, 4, 1. And the same thing happens to the 2. 6, 5, 4, 2, and 1. 6, 5, 4, 2, 1. And then the 3. 6, 5, 4. And then the 3 gets inserted, and then the 4 and the 5 are all pushed. Let's take that bad boy. Actually, I'm going to take it with its description of the figure here for our notes. If you guys want access to these notes, they are live on my GitHub right now in the description. You guys can follow along as I push these on my stream and kind of get like the spark notes, I guess, of the book. Okay, so the operation of insertion sort of index array of items n, where A initially contains the sequence and n equals to 6, the array indices appear above the rectangles, and the values stored in the array positions appear within the rectangles. A through E, the iterations of the for loop of lines 1 through 8, right? Those are just the iterations of the for loop. In each iteration, the blue rectangle holds the key taken from A index of I, which is compared to the values in the tan rectangles to the left of the line of test, to the left in the test of line 5. Orange arrows show the array values moved 1 position to the right in line 6, and blue arrows indicate where the key moves to in line 8. And then in F, the final sorted array. At the start of each iteration of the for loop, lines 1 through 8, the subarray A index of 1 up to I less than 1 consists of elements originally in A index of 1 up through I less than 1, but now in sorted order. Loop invariants help us understand why an algorithm is correct. When you're using a loop invariant, you need to show 3 things. Initialization. Okay, so loop invariant, we have 3 things. Number 1, initialization. Number 2, maintenance, and number 3, termination. Okay, so what exactly was a loop invariant? In fact, elements that are originally are now a loop invariant. Okay, so let's quickly query the orb here. Can you explain what a loop invariant is for algorithms? A loop invariant is a condition or logical statement that is true before and after every iteration of a loop. It is used to prove correctness of an algorithm. You show the invariant is true at the start. You show it remains true at each time the loop runs. Then, when the loop ends, the invariant helps you conclude something useful. Okay, so then, like, what is a definition of it? A loop invariant is a property or condition that is true before the loop begins, remains true before and after each iteration of the loop, and helps to show correctness when the loop terminates. I like that. That's a good definition. Loop invariant, right? So these just these kind of facts or these characteristics or properties of the algorithm that kind of should remain true throughout the process of it. And if any of these deviate, you know our algorithm is incorrect. Like an incorrect algorithm, quote unquote, as they mentioned in chapter 1, right? Hey, Chill Beats Cafe, how's it going? I appreciate you joining me. Hey, Tim, pull out the deck of cards. Yo, Mike, they have OpenAI Codex extension of VS Code now. Yeah, I haven't put a AI in my extension in my code. I'm kind of avoiding that. I want to just, if I need to go to it, I'll go to it, but I think it might be too easy having it right there. Okay, initialization. it is true prior to the first iteration of the loop, right? Why does it keep doing that? Right? Maintenance. If it is true before an iteration of the loop, it must remain true before the next iteration. Interesting. What's going on here? Okay. If it is true before an iteration of the loop, it remains true before the next iteration. And termination. The loop terminates, and when it terminates, the invariant, usually along with the reason that the loop terminated, gives us a useful property that helps show us the algorithm is correct. When the first two properties hold, the loop invariant is true prior to every iteration of the loop. Of course, you are free to use established facts other than the loop invariant itself to prove that the loop invariant remains true before each iteration. A loop invariant proof is a form of mathematical induction, where to prove that a property holds, a loop invariant proof is a form of mathematical induction, where to prove that a property holds, you prove a base case and an inductive step. Here, showing that the invariant holds before the first iteration corresponds to the base case, and showing that the invariant holds from iteration to iteration corresponds to the inductive step. The third property is perhaps the most important one, since you are using the loop invariant to show correctness. Typically, you use the loop invariant along with the condition that caused the loop to terminate. Mathematically, induction typically applies the inductive step infinitely, but in a loop invariant, the induction stops when the loop terminates. I'm going to ask for a little bit more clarity on this guy. Can you give a little insight on this, as I'm having a little trouble following? A loop invariant proof works just like a mathematical induction. You have a base case, which shows the invariant is true before the loop starts. You have an inductive step, which is the maintenance. And then you have termination when the loop finally stops, the invariant plus the loop stopping condition. So why is this like induction? In induction, you prove property for all integers starting at 0 or 1. In loop invariance, you prove a property for all iterations of a loop. First iteration equals a base case. Second, each iteration preserves truth equals an inductive step, and stop at a loop end instead of going to infinity. Interesting. Let's see how these properties hold together for insertion sort. Initialization. This will be good to see an example. We start by showing that the loop invariant holds before the first loop iteration when I is equal to 2. The subarray, right, I is going to be equal to 2 because the subarray of the array A, which we are going to be sorting into, right, we're not creating a new array in memory, we're just using the first index as kind of like a starting place of a subarray within A to sort on. Think of it like both of your hands are the array in total, where one hand has the deck and one hand has just the first card in it. And as you feed cards to your left hand and you sort them using insertion sort, that is the entire array, right? And then you're just using, the left hand is just a portion of it that you're just using to conserve memory, right? In a clever way. The subarray A index 1, right? This is not 0 index, this is 1 index, through I minus 1 consists of just the single element A index of 1, which is the first element, which is in fact the original element in A index 1, right? The first element in the original array is the first element in the subarray before the loop starts. Moreover, this subarray is sorted. After all, how could a subarray with just one value not be sorted? Exactly, right? 10 by itself is sorted. 10. which shows that the loop invariant holds prior to the first iteration of the loop, maintenance. Next, we tackle the second property, showing that each iteration maintains the loop invariant. Informally, the body of the for loop works by moving the values in A, index of I less than 1, A, index of I less than 2, A, index of I less than 3, and so on by one position into to the right, right? We increase the value, we move that value to the right in the array until we satisfy a property, or satisfy the proper position for the current value that we're on, A, index of I. At which point it is inserted at the value of A, index of I. The subarray A index of 1 through I then consists of elements originally in A index of 1 through I, but now in sorted order. Incrementing I, increasing the value by 1 for the next iteration of the for loop, then preserves the loop invariant. A more formal treatment of the second property would require us to state and show a loop invariant for the while loop of lines 5 through 7. Let's not get bogged down in such formalism just yet. Instead, we'll rely on the informal analysis to show that the second property holds for the outer loop. So it's just it's not going to try and go into this nested loop. It's going to just give us the broad overview here, I guess. Termination. Finally, we examine the loop termination. The loop variable I starts at 2 and increases by 1 in each iteration, right? Once i's value exceeds n, or the number of items that we have in line 1, the loop stops or terminates. That is, the loop terminates once I equals to n plus 1, right? Or we'll have an index error. Substituting n plus 1 for I in the wording of the loop invariant yields that the array A1 through n consists of the elements originally in A1 through n, but in sorted order. Hence, the algorithm is correct. So I want to see here, so you go on the last item, you do sort it, and now you increase to plus 1 because you have 6 items. So I would equal to 7 and terminate. So you don't insert on the termination, right? You go up to n, perform the last loop iteration through the nested while to find the insertion, and then terminate on 7. Hey, we got 24 people in here. If you guys are enjoying, I appreciate you being here. We're reading Introduction to Algorithms 4th edition. This is the CLRS. Those are the authors, the acronyms of their last name. So thank you guys so much for being here. We're reading Chapter 2. I am recording, and I'll be chopping this up just like I did for Chapter 1 and posting them back to the channel, kind of like in an audiobook style for you guys to listen to over and over again and get more practice with this if you want. I sure will be. I was looking for audiobooks of this to listen to while we stream, so I didn't have to read it aloud, but I didn't really find anything. And I looked at some AI options, but they were just too robotic, and so we're reading it, which is good anyways. Okay, pseudocode conventions. We use the following conventions in our pseudocode. Indentation indicates block structure. For example, the body of the for loop that begins on line 1 consists of lines 2 through 8, and the body of the while loop begins on line 5 consisting of lines 6 through 7. Okay, they're just showing you their styles for pseudocode. Our indentation style applies to if-else statements as well. Using indentation instead of textual indicators or block structure, such as beginning and end statements or curly braces, reduces clutter. Right? They're using kind of Python syntax here. The looping structure while, for, and repeat until, and if-else conditional structs have interpretations similar to those in C, C++, Java, Python, and JavaScript. In this book, the loop counter retains its value after the loop is exited, unlike some situations that arise in C++ and Java. Thus, immediately after a for loop, the loop counter's value is the value that Thus, immediately after a for loop, the loop counter's value is the value that first exceeded the for loop bound. We use this property in our correctness argument for insertion sort. Oh, okay, so it's saying, I think what it's saying is that in C, Java, and potentially Python. Python might have some sort of garbage collection going on for this. I'm not exactly sure, but it sounds like for C at least, not Java. C, if you were to go to that place in memory, right? If you were to visit that place in memory after the loop ends, even though that variable isn't being used, I think that the value is still there. It's not like gone, right? I'm not exactly sure. I might need to look that up. What do you guys think? If you guys have any opinions or knowledge on that front. The for loop header in line 1 is for I equals 2 to n. And so when this loop terminates, I equals to n plus 1, or the number of items plus 1. When we use the keyword to when a for loop increments its loop counter to in each iteration, and we use the keyword down to when a for loop decrements its loop counter, reducing its value by 1 in each iteration. When the loop counter changes by an amount greater than 1, the amount of the change followed by the optional keyword by. Okay, it's just showing you how it's going to basically describe its pseudocode. The symbol // indicates that the remainder of the line is a comment. Variables such as I, J, and key are local to the given procedure. We won't use global variables without explicit indication. We access array elements by specifying the array name followed by the index in square brackets. For example, a index of I indicates the ith element of the array A. Although many programming languages enforce zero-origin indexing, bing, 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 here we go. This is why they're going to explain it here. Enforce zero-origin indexing for arrays. 0 is the smallest valid index. We choose whichever indexing scheme is clearest for human readers to understand. Because people usually start at counting at 1, not 0, most, but not all, the arrays used in this book use one-origin indexing. I kind of don't like that. I like how CS50, how they teach you zero indexing from the start, because then it's just like ingrained in you from the jump. Like it was pretty challenging at first to kind of get my mind to like think in zero indexing rather than one indexing. But once I started thinking in zero indexing, I was smooth sailing. At least for starting to understand loops and nested loops and start solving LeetCode problems. But what do you guys think? Do you like how do you think it's nice that they did it by one index for accessibility, or do you think accessibility for programmers should be zero index? What do you guys think? Hey, Bino Ames, how's it going? Appreciate you for coming in. Okay. That is because a Python for loop iterates through a list. Okay, hold on. Sorry. To be clear about whether a particular algorithm assumes zero origin or one origin indexing, we'll specify the bounds of the array explicitly. If you are implementing an algorithm that we specify using one origin indexing, but you're writing in a programming language that enforces zero origin indexing, then give yourself credit for being able to adjust. You can either always subtract 1 from the index or allocate in each array with 1 extra position and just ignore 0. Why would you do that? Why? Just adjust it. I don't know. The notation quote colon denotes a subarray. Thus, a subarray of I through j indicates a subarray of A consisting of elements A index of I plus 1, all the way up to A index of j. We also use this notation to indicate the bounds of an array we did earlier when discussing A index of 1 all the way up to n. We typically organize compounded data into objects, which are composed of attributes. We access a particular attribute using the syntax found in many object-oriented programming languages. Okay, so let's go here. Objects. Which are composed of attributes. We access a particular attribute using the syntax found in many object-oriented programming languages. The object name followed by a dot followed by the attribute name. For example, If an object X has an attribute F, we denote this by X dot F. So just dot notation, right? So methods, class methods, so pretty easy stuff. We treat a variable representation representing an array or object as a pointer, known as a reference in some programming languages, to the data representing the array or object. For all attributes F of an object X, setting Y equal to X causes F dot Y to equal X dot F. Or sorry. For all attributes, F of an object X, setting Y equal to X, right, an alias, causing y.f to equal x.f. Moreover, if we now set x.f to 3, then afterward, not only does x.f equal 3, but y.f also equals to 3. In other words, x and y point to the same object other than after the assignment, y equals to x. This way of treating arrays and objects is consistent with most contemporary programming languages. So this is like if you read through, lists, and I think they talk about this in Python Crash Course. They also talk about it in Fluent Python, where aliasing of list elements, where you objects within or in lists in Python and stuff like that are references to the objects in memory, and then you can assign an alias to the array and modify the array on that alias. So just like my name is Michael, I also go by Mike, and I respond the same way in both ways, by Michael or Mike. So it's kind of like the same way, right? I have an attribute of age of 26. Mike is 26 and Michael is 26, and they're the same thing. So Mike.age equals 26. Michael.age equals 26. Michael equals Mike, right? Our attribute notation can cascade. For example, suppose that attribute F is itself a pointer to some type of object that has an attribute G. Oh, interesting. So you can have even like nesting object pointers. So suppose that attribute F is itself a pointer to some object that has an attribute G. Then the notation is x.f.g is implicitly parenthesized as x.f.g. In other words, if we had assigned y equals to object x with some method f, then x.f.g is the same as y.g. Sometimes a pointer refers to no object at all. In this case, we give it a special value of nil. We pass parameters to a procedure by value. The call procedure receives its own copy of the parameters, and if it assigns a value to a parameter, the change is not seen by the calling procedure. When objects are passed, the pointer to the data representing the object is copied and the object attributes are not. For example, if x is a parameter of a called procedure, the assignment x equals to y within the call procedure is not visible to the calling procedure. The assignment, x.f equals to 3, however, is visible if the calling procedure has a pointer to the same object as x. Similarly, arrays are passed by pointer, so that a pointer to the array is passed rather than the entire array. And changes to the individual array elements are visible to the calling procedure. So this is kind of just a little bit kind of like on this idea that you can have a pointer of like an array, and then you can put that array, like let's say within like a tuple, and then you can modify the memory object within the tuple, and it will both reflect the modified object in the tuple and the actual object itself modified. So if you're modifying the pointer, if you're just having things by reference, and then you actually what's the value called where you follow the pointer? Dereference? Where you dereference? Is that what it is called? I can't remember from CS50. It's been like 6 or 8 months. When you dereference and then you modify, every place where that pointer is referenced in other objects, I think is also impacted, is basically what this means. So let me go ahead and just copy this really quick. I'm going to say my interpretation of this is kind of like if we have like nested data structures of like a list within a tuple. If the list object is modified, that is a reference to the list in memory, and the list is modified both within the tuple and with the actual list itself. This is kind of just hitting the home that you can nest memory pointers within objects and they are changed globally throughout the system, correct? Exactly, you're on the right track. Let me cleanly connect what this is saying. Call by value, always true in the CLRS model. When you call a procedure, the parameter itself is copied. So if you reassign the parameter x equals y inside the procedure, the reassignment is local, the caller never sees it. But with objects like arrays, lists, records, and structs, okay, so when you pass something by reference, um, and get the actual object itself, then I think it happens locally. Okay, so what actually gets copied is the pointer reference to the object in memory. That means the called procedure and the caller are both pointing to the same underlying object. So if you rebind the variable inside the function x equals y, the caller doesn't see the change. If you mutate the object that x points to, the caller does see it because both copies of the pointer refer to the same object in memory. Your analogy with the list inside of a tuple is perfect. It's a perfect mental model. The tuple T itself is immutable, and you can't swap out elements directly, but the list inside the tuple is mutable, and both T and U share the same pointer to that list. So modifying the list through U shows up when accessing it through T. In simpler words, assignments are local. Rebinding X doesn't affect the color. Mutations are global. Got you. Hey Cafe, how's it going? Yeah, I started with Harvard CS50P. I started building some independent projects and reading books, and then I jumped into Harvard CS50X, and then I did, some more projects and book reading stuff, and then I've been reading books, and now we're taking MIT 6002, and we're going to be getting into some more challenging stuff here shortly, hopefully. I don't know. We'll see. Okay. A return statement immediately transfers control back to the point of call in the calling procedure. Most return statements also take a value to pass back to the caller, or our pseudocode differs from many programming languages in that we allow multiple values to be returned in a single return statement without having to create objects to pack them together. The Boolean operators and or are short-circuiting. That is, evaluating the expression x and y by first evaluating x. If x evaluates to false, then the entire expression cannot be evaluated to true. Therefore, y is not evaluated. If, on other hand, x evaluates to true, y must be evaluated to determine the value of the entire expression. Similarly, if the expression is x or y, the expression y is evaluated only if x evaluates to false. True short-circuiting operators allow us to write Boolean expressions such that x does not equal nil and x.f equals to y without worrying about what happens upon evaluating x.f when x is nil, right? Because so what it's short-circuiting means is that shout out to Mahan if he's in here. He hasn't been in here in quite a while. For actually, he taught us what short-circuiting was through the chat here um, when we were doing some LeetCode problems. So with these expressions and or, it goes kind of like logically as you would read it left to right in English. So you would first evaluate the x value here in the and statement and the x value in the or statement, right, wherever that is. And if that first conditional check over that value doesn't evaluate to true to then extend across the rest of the and or statement, then there is no check on the second conditional. So you can first, you can kind of short circuit these and or operators by specifying the nil conditional up front and saying, okay, I'm not going to, don't access an index, right, of this array if some value is none, or if I is, past a certain value, right? You can kind of, um, you know, work around kind of certain errors cleverly, I don't know, in this way, if you've ever worked with these. Um, the keyword error indicates that an error occurred because conditions were wrong for the procedure to have been called, and the procedure immediately terminates. The calling procedure is responsible for handling the error, and so we do not specify what action to take. Okay, so there's some exercises here that we'll come back and complete later. Let's just keep reading here. We need to keep reading. All right, analyzing algorithms. And analyzing an algorithm has come to mean predicting the resources that the algorithm requires. You might consider resources such as memory, communication, bandwidth, or energy consumption. Most often, however, you'll want to measure computational time. If you analyze several candidate algorithms for a problem, you can identify the most efficient one. There might be more than just one viable candidate, but you can often rule out several inferior algorithms in the process. Before you can analyze an algorithm, you need a model of the technology that it runs on, including the resources of that technology in a way to express the costs. Most of this book assumes a generic one processor random access machine model of computation as the implementation technology, with the understanding that algorithms are implemented as computer programs. In the RAM model, instructions execute one after another with no concurrent operations. The RAM model assumes that each instruction takes the same amount of time as any other instruction, that each data access using the value of a variable or storing into a variable takes the same amount of time as any other data access. In other words, in the RAM model, each instruction or data access takes a constant amount of time, even indexing into an array. Okay, so we have analyzing, or we have the random RAM model, which is the random access machine. Okay. Strictly speaking, we should precisely define the instructions of the RAM model and their costs. To do so, however, would be tedious and yield little insight into algorithm design and analysis. Yet we must be careful not to abuse the RAM model. For example, what if a RAM had instructions that sorts? Then you could sort in just one step. What's going on? Sorry. Strictly speaking, we should precisely define the instructions of the RAM model and their cost. To do so, however, would be tedious and yield little insight into algorithm design and analysis. Yet we must be careful not to abuse the RAM model. For example, what if a RAM had an instruction that sorts? Then you could sort in just one step. Such a RAM would be unrealistic since such instructions do not appear in real computers. Our guide, therefore, is how real computers are designed. The RAM model contains instructions commonly found in real computers. Arithmetic, such as add, subtract, multiply, divide, remainder, floor, ceiling, data movement, load, store, copy, and control, conditional, unconditional branch, subroutine call, and return. The data types in the RAM model are integer, floating point for storing number approximations, and character. Real computers do not usually have a separate data type for the Boolean values true and false. Instead, they often test whether an integer value is 0, false, or non-zero, true, as in C. Although we typically do not concern ourselves with precision for floating point values in this book, many numbers cannot be expressed exactly in floating point. Precision is crucial for most applications. We also assume that each word of data has a limit on the number of bits. For example, when working with an input size of n, we typically assume that integers are represented by c times log base 2 of n bits, or some constant c is greater than or equal to 1. We require that c be greater than or equal to 1 so that each word can hold the value of n, enabling us to index the individual. Um, okay, got you. You don't want to factor down the constant, right? You need to be greater than or equal to 1 because you have to at least hold the value of n within of the word, right? The word or the bytes that contain the word. If the word size can grow arbitrarily, we could store huge amounts of data in one word and operate on an all constant time, an unrealistic scenario. Real computers contain instructions not listed above, and such instructions represent a gray area in the RAM model. For example, in exponentiation, a constant time is for example, is exponentiation a constant time instruction? In the general case, no. To compute x to the power of n, when x and n are general integers, typically takes time logarithmic in n. And you must worry about whether the results fit into a computer world. If n is an exact power of 2, however, exponentiation can usually be viewed as a constant time operation. Many computers have a shift left instruction, which in constant time shifts the bits of an integer by n to the left. In most computers, shifting the bits of an integer by one position to the left is equivalent to multiplying by 2. So that shifting by the bits by n positions to the left is equivalent by multiplying by 2 to the power of n. Therefore, such computers can compute 2 to the n in one constant time instruction by shifting the integer 1 by n positions to the left, as long as n is no more than the number of bits in a computing word in a computer word. We'll try to avoid such gray areas in the RAM model and treating computing 2 to the power of n and multiplying by 2 to the power of n as constant time operations when the result is small enough to fit in the computer world. Basically, I think they're just kind of setting up the idea for asymptotic notation and getting into the idea of exponentiation and, all this stuff. So the RAM model does not account for the memory hierarchy that is common in contemporary computers. It models neither caches nor virtual memory. Several other computational models attempt to account for memory hierarchy. I can never say that word. Memory hierarchy effects, which are sometimes significant in real-world problems on real machines. Section 11.5 and a handful of problems in this book examine memory hierarchy effects, but for the most part, the analysis of this book do not consider them. Models that include the memory hierarchy are quite a bit more complex than the RAM model, and so they can be difficult to work with. Moreover, RAM model analyses are usually excellent predictors of performance on actual machines. Although it is often straightforward to analyze an algorithm in the RAM model, sometimes it can be quite a challenge. You might need to employ mathematical tools such as combinatorics, probability theory, algebraic dexterity, and the ability to identify the most significant terms in a formula. Because an algorithm might behave differently for each possible input, we need a means for summarizing that behavior in simple, easy understood formulas. Analysis of insertion sort. How long does insertion sort procedure take? One way to tell would be for you to run it on your computer and time for how long it runs. Of course, you'd first have to implement it in a real programming language. Since you cannot run our pseudocode directly, what would such a timing test tell you? Would you find out how long insertion sort takes to run on your particular computer, on that particular input, under the particular implementation that you created, with the particular compiler or interpreter that you ran, with the particular libraries that you linked in, and with the particular background task that you're running on your computer concurrently with your timing tests? If you run insertion sort again on your computer with the same input, you might get even different timing results. From running just one implementation of insertion sort on just one computer and on just one input, what would you be able to determine about insertion sort's running time if it were given in a different input? if you were able to run it on a different computer or if you're able to implement it in a different language. Not much. We need a way to predict, given a new input, how long insertion sort should take. So this is really kind of prefacing into the idea of the asymptotic notation, right, for algorithms and how we can define algorithms and their running time based off of this kind of best case, worst case scenario, and big O, big omega, and then big theta, um, and because each computer, depending on the tasks, the hardware, the conditions, environment, input, whatever, will run then input not the same every single time. It's kind of like humans in a way that it won't produce the same thing every single time, but it gets fairly close. Like, Steph Curry is really can shoot really accurately, and but his shot is a little bit different. It's pretty much nearly the same every single time. That's why he's able to be super accurate with that muscle memory. But it's impossible to replicate the exact same force, the exact same stretch or whatever, torque, rotation every single time. Now it's all within certain margins of error, and that's why he is a professional. And if you kind of think about it that way, and so, but now there is probably scenarios where you do shoot the basketball if you were to calculate all those statistics the same way, and that's just random odds. But the odds of doing that is incredibly low. So in theory, yeah. Anyways, let's keep going. Instead of timing a run or several runs of insertion sort, we can determine how long it takes by analyzing the algorithm itself. We'll examine how many times it executes each line of pseudocode and how long each line of pseudocode takes to run. We'll first come up with a precise but complicated formula for running time. Then we'll distill the important part of the formula using convenient notation that can help us compare the running times of different algorithms for the same problem. How do we analyze insertion sort? First, let's acknowledge that the running time depends on the input. You shouldn't be terribly surprised that sorting 1,000 numbers takes longer than sorting 3 numbers. Moreover, insertion sort can take different amounts of time to sort 2 input arrays of the same size, depending on how nearly sorted they already are. Even though the running time can depend on many features of the input, we'll focus on the one that has been shown to have the greatest effect, namely the size of the input, and describing the running time of a program as a function of the size of its input. Right? So this kind of just probably said that, like, if you have, two arrays of the same length that you're going to sort, well, one could be sorted in a preconceived notion already, or like a already in a little bit more optimized way. Like, let's say it starts with 1, 2, 3, and it goes like 10, 4, 5, right? And then the next one is just completely random, like 10, 20, 1, 2, 6. Like, so the first one is pretty much almost already in order. So there's like some worst case times, but there's also that it could take, but not in all cases. Like in the worst possible scenario. We also need to be clear about whether we are discussing the running time of an input that elicits the worst case behavior, the best case behavior, or some other case. Hey Harry, how's it going? Hey Shabanash, what's going on, my guys? What's going on, everybody? Welcome back in. Leave a like if you're here. I appreciate everybody for being here. Let's keep going. We're reading Introduction to Algorithms, CLRS, 4th edition. We're in chapter 2. We're chugging along here really nicely. The best notion for input size depends on the problem being studied. For many problems such as sorting or computing discrete Fourier transformations, the most natural measure is the number of items in the input. For example, the number n of items being sorted. For many other problems such as multiplying two integers, the best measure for input size is the total number of bits needed to represent the input in ordinary binary notation. Sometimes it is more appropriate to describe the size of the input with more than just one number. For example, if the input to an algorithm is a graph, we usually characterize the input size by both the number of vertices and the number of edges in the graph. We'll indicate which input size measure is being used with each problem we study. The running time of an algorithm on a particular input is the number of instructions a data and data access executed. So running time of a particular algorithm is the number of instructions and data accesses executed. How we account for these costs should be independent of any particular computer, but within the framework of the RAM model. For the moment, let us adopt the following view. A constant amount of time is required to execute each line of our pseudocode. One line might take more or less time than another, but we'll assume that each execution of the kth line takes c sub k time, where c is some constant, right? It's just saying that each line of our pseudocode, of our insertion sort algorithm, which is represented by k, takes some amount of time denoted as c. So the amount of time that that line took is c sub k. This viewpoint is in keeping with the RAM model and it also reflects how the pseudocode would be implemented on most actual computers. Let's analyze the insertion sort procedure as promised. We'll start by devising a precise formula that uses the input size and all the statement costs c sub k. This formula turns out to be messy, however. Right? We'll then switch to the simpler notation that is more concise and easier to use. This simpler notation makes clear how to compare the running times of algorithms, especially as the size of the input increases. To analyze the insertion sort procedure, let's view it on the following page, with the time cost of each statement and the number of times each statement is executed. For each I, 2, 3, up to n, let's denote t sub I. Let t sub I denote the number of times the while loop test in line 5 is executed for that value of I, right? So in each insertion sort, we have that nested for loop that checks conditionally where we're going to insert within the subarray of sorted numbers. And so we are going to let t sub I denote the number of times that inner loop happened. Hey Blaze, how's it going? I mainly program in Python, but we are reading just a more general introduction to algorithms, 4th edition right now. Because comments are not executable statements, assume that they take no time. When a for or a while loop exits the usual way, because the test loop comes out false. Okay, gotcha. The running time of the algorithm is the sum of the number of times each statement executed. A statement that takes ck steps to execute m times contributes to ck times m, the total running time, right? Each individual running to each step times the number of executes. We usually denote the running time of an algorithm of an instance size n by t sub n. To compute t sub n, the running time of insertion sort on an input of n values, we sum the product costs and times columns obtaining, right? So you have costs and the times. You have this big long formula here. So all the way up until constant C5 n minus 1. Interesting. Even for inputs of a given size, an algorithm's running time may depend on which input of that size is given. For example, in insertion sort, the best case occurs when the array is already sorted. In this case, each time that line 5 executes, the value of the key is the value of the originally a sub I that's already greater than or equal to all the values because it's already sorted. So in the best case scenario, if you have an array, it's already sorted. It doesn't need to be sorted, so it just takes a single scan through and it's done, right? Just to check that it's already sorted. So that while loop always exits upon the first line in line 5. Therefore, we have t sub I is equal to 1 for all i's up to 2 through n. And the best case running time is given by this notation here. We can express this running time as a times n plus b for constants a and b that depend on the statement costs of c sub k, where A is equal to all the constants and B 1, 2, 3, 4, 5, and 8, and B is equal to constants 2, 4, 5, and 8. The running time is thus a linear function of n. The worst case arises when the array is in reverse sorted order. That is, it starts out in decreasing order. The procedure must compare each element I with each element in the entire sorted subarray. And so T sub I equals to I for I 2, 3, all the way up to n. The procedure finds that A index of j, which is greater than the key every time in line 5, and the while loop exits only when j reaches 0. So j, has to run I minus 1 times on each pass. So the sum of all i's up through I. Yeah, this is that equation that we've seen before. I'm probably going to need to take a closer look at these equations and actually see what's kind of going on here. Or for the sake of time, we're kind of just moving on. We can express, because I'm following verbally, but the math behind it is a little bit funky. We can express this worst case running time as an a times n squared plus bn plus c for constants a, b, and c that again depend on the statement costs, right, of that individual row or that individual step. Now, a equals c sub 5 divided by 2 plus c sub 6 divided by 2 plus c sub 7 divided by 2, and b equals c1, c2, c4, c5 divided by 2 minus, okay, quadratic function. Typically, as in insertion sort, the running time of an algorithm is fixed for a given input, although we see some interesting randomized algorithms whose behavior can vary even for a fixed input. Worst case and average case analysis. Oh no, not the bot. Our analysis of insertion sort looked at both the best case in which the input array was already sorted and the worst case in which the input array was reverse sorted. For the remainder of this book, we'll usually, but not always concretely, only find the worst case running time, that is, the longest time running time for any input of size n. Why? Here are 3 reasons. The worst case running time for an algorithm gives an upper bound on the running time for any input. If you know it, then you have a guarantee that the algorithm never takes any longer. If you need not make some educated guess about the running time and hope it never gets much worse. This feature is especially important for real-time computing, which operations must be completed by a deadline. For some algorithms, the worst case occurs fairly often. For example, in searching a database for a particular piece of information, the searching algorithm's worst case often occurs when the information is not present in the database. It has to exhaust the search, searching through every item to see if it is that item, and if it's not that item, that's the worst case because it had to search through every item n times. In some applications, searches for absent information may be frequent. The average case is often roughly as bad as the worst case. Suppose that you run insertion sort on an array of n randomly chosen numbers. The average case is often roughly as bad as the worst case. Suppose that you run insertion sort on an array of n randomly chosen numbers. How long does it take to determine where subarray I or a index of 1 through I minus 1, so the sorted subarray, is insert the current element? On average, half the elements in the subarray are less than the current element and half are greater on average. So on average, therefore, the current element is compared with just half of the subarray, and so T sub I is about I divided by 2. The resulting average case running time turns out to be a quadratic function of input size, just like the worst case running time. Okay. In some particular cases, we'll be interested in the average case running time of an algorithm. We'll see this technique probabilistic analysis applied to various algorithms throughout this book. The scope of the average case analysis is limited because it may not be apparent what constitutes an average input for a particular problem. Often, we'll presume that all inputs of a given size are equally likely. In practice, this assumption may be violated, but we can sometimes use a randomized algorithm, which makes random choices to allow for probabilistic analysis and yield an expected running time. We explore randomized algorithms more in Chapter 5. Order of growth. In order to ease our analysis of the insertion sort procedure, we use some simplifying abstractions. First, we ignore the actual cost of each statement using the constants c sub k to represent these costs. Still, the best case and worst case running times in equations 2.1 and 2.2 are rather unwieldy. Unwieldy? Is that how you pronounce it? The constants in these expressions give us more detail than we really need. That's why we also express the best case running time as a times n plus b for constants a and b that depend on the statement costs of c sub k, and why we express the worst case running time as a times n squared plus b times n plus c for constants a, b, and c that depend on the statement costs. We thus ignored not only the actual statement costs, but also the abstract costs c sub k. Let's now make one more simplifying abstraction. It is the rate of growth, or order of growth, of the running time that really interests us. We therefore consider only the leading term of a formula, e.g. a n squared, since the lower order terms are relatively insignificant of large values of n. We also ignore the leading term's constant coefficients, since constant factors are less significant than the rate of growth in determining computational efficiency for large inputs. For insertion sort worst case running time, we ignore the lower order terms and the leading term's constant coefficient. Only the factor of n squared from the leading term remains. The factor n squared is by far the most important part of the running time. For example, suppose that an algorithm implemented on a particular machine takes n squared divided by 100 plus 100n plus 17 microseconds of an input size n. Although the coefficients of 1 over 100 for the n squared terms and 100 for the n term differ by 4 orders of magnitude, the n squared divided by 100 term dominates the smaller 100 times n term once and exceeds 10,000. Although 10,000 might seem large, it is smaller than the population of an average town. Many real-world problems have much larger input sizes. To highlight the order of growth of the running time, we have a special notation that uses Greek letter theta. Right? So I'm going to do so I need to theta. How do I theta hotkey Mac? Option plus J. No. Option O. No. Where are you? Come out wherever you are. Not any of those. um Okay. I'll have to. I don't want to have to come back, but we might have to. Yeah, give me theta. Give me theta. Give me theta. Right, theta. To highlight the order of growth of the running time, we have a special notation that uses the Greek letter theta. We write the insertion sort as a worst case running time of theta n squared. Theta highlights the order of growth of the running time theta of n squared, or just theta n squared. We also write the insertion sort has a best case running time of theta of n, or theta n. Best case running time of theta of n? Is theta best case? No. I think theta is the tight bound. Is bounded by below and above by the same function, so it's thus the theta of, okay. Okay, for now, think of theta notation as saying roughly proportional when n is large, so that theta n squared means roughly proportional to n squared when n is large, and theta n means roughly proportional to n when n is large. We'll use theta notation informally in this chapter to find it precisely in chapter 3. We usually consider one algorithm to be more efficient than another if the worst case running time has a lower order of growth due to constant factors and lower order terms. An algorithm whose running time that has a higher order of growth might take less time for small inputs than an algorithm whose running time has a lower order of growth. But on large enough inputs, an algorithm whose worst case running time is theta of n squared, for example, takes less time than the worst case running time of an algorithm whose worst case is theta of n cubed. Regardless of the constants hidden by the theta notation, there's always some number of n sub 0 such that all input sizes n that are greater than n sub 0, the theta of n squared algorithm beats theta of n squared cubed algorithm in the worst case. So take this theta notation. So theta notation highlights the order of growth of the running time. Normally, in formal asymptotics, O of n squared is upper bound, omega n squared is a lower bound, and theta n squared is both upper and lower bound. So strictly speaking, it doesn't make any sense to say best case running time is theta n. That's mixing the idea of input case analysis. But the CLRS, this book is just saying informally the best case algorithm behaves like theta of n. The worst case, they're using theta here as roughly proportional to not the full rigorous definition that comes in chapter 3. Best case complexity of insertion sort is theta n linear when it's already sorted. Yeah. Okay, I'll come back and do these problems later. I'm going to keep reading here. We're almost done with the chapter here. Got a couple more pages. 2.3, designing algorithms. You can choose from a wide range of algorithm design techniques. Insertion sort uses the incremental method. For each element AI inserted into its proper place into the subarray, already having sorted the subarray. This section examines another design method known as the divide and conquer, which we explore in more detail in Chapter 4. We'll use divide and conquer to design a sorting algorithm whose worst case running time is much less than the insertion sort. One advantage of using an algorithm that follows the divide and conquer method is that analyzing its running time is often straightforward using techniques that we'll explore in Chapter 4. The divide and conquer method. So divide and conquer method. Many useful algorithms are recursive in structure. To solve a given problem, they call themselves on one or more times to handle closely related subproblems. These algorithms typically follow the divide and conquer method. They break the problem into several subproblems that are similar to the original problem, but smaller in size. Solve the subproblems recursively, but smaller in size. Solve their problems recursively, and then combine these solutions to create a solution to the original problem. In the divide and conquer method, if the problem is small enough, the base case, you just solve it directly without recursing. Otherwise, the recursive case, you perform 3 characteristic steps. Divide the problem into one or more subproblems that are smaller instances of the problem. Conquer the problems by solving them recursively. Combine the subproblem solutions to form a solution to the original problem. So you go, number 1 is divide. Number 2 is conquer. Number 3 is combine. Okay. The merge sort algorithm closely follows the divide and conquer method. Merge sort. In each step, it sorts a subarray, A, P through R, starting with the entire array, A, 1 through N, and recursing down to smaller and smaller subarrays. Here's how merge sort operates. Divide the subarray, A, P through R, to be sorted into 2 adjacent subarrays, each of half the size. To do so, compute the midpoint, Q, of the subarray, taking the average of P and R and dividing the value, the length, into subarrays. PQR, P through Q, and Q plus 1 through R. Conquer by sorting each of the two subarrays, A, P through Q, and A, Q plus 1 through R, recursively using merge sort. Combine by merging the 2 sorted subarrays back into a P through R, producing the sorted answer. Sorts a subarray. So merge sort. Sorts a subarray, A, P through R, starting with an entire array of A, 1 up through N. And recursing down to smaller and smaller subarrays. Here's how merge sort operates. Okay, I'm going to take a screenshot of the divide and conquer here. Okay. The recursion bottoms out. It reaches the base case when the subarray P through R is to be sorted has just one element. That's the base case. That is, when P equals to R, as we noted in the initialization argument for insertion sorts loop invariant, a subarray comprising of just a single element is always sorted. The key operation of the merge sort algorithm occurs in the combine step, which merges 2 adjacent sorted subarrays. The merge operation is performed by the auxiliary operation merge A array P, Q, R on the following page, where A is an array, P, Q, and R are indices into the array such that P is less than or equal to Q, which is less than R. The procedure assumes that the adjacent subarrays A, P through Q, and A, Q plus 1 through R, right, the adjacent, the divided subarrays that you have, um, were already recursively sorted. It merges the two sorted subarrays to form a single sorted subarray that replaces the current subarray. To understand how merge sort procedure works, let's return to our card playing motif. Suppose that you have two piles of cards face up on a table. Okay, two piles of cards face up. Each pile is sorted with the smallest value on top. Okay, so you have, okay, got you. You wish to merge the two piles together into a single sorted output pile, which is to be face down on the table. Okay, so you have two piles face up in sorted order. We're going to try to combine them face down. The basic step consists of choosing the smaller of the two cards on top, face up piles. So if you have a 2 and let's say a 5, we pick up the 2. Removing it from its pile, which now exposes a new top card, and placing this card face down on the output pile. So 2 goes down. Okay. Now we have we have 5 and a 4. Now repeating this until one or more input piles empty, in which you just take the remaining input pile and flip it over into, okay, you just keep going until you have one pile. Ah, okay, we should do that actually with some cards. We should do these algorithms. I think it would be kind of fun. I should go get a deck of cards tomorrow on stream. Right, so you just, okay, we have a 2 and a 5. Okay, we take the 2, goes down. That reveals a 4. Okay, the 4 and the 5. 4 goes down. That reveals a 6. Okay, we have a 6 and a 5. The 5 goes down. We have an 8. The 6 and the 8. The 6 goes down. Right? Okay, this pile's gone. We pick up this pile, and now we merge. Now we sort again. And we keep going until we have just one pile. We wish to merge the two piles into a single sorted output pile face on the table. Placing this card face down the output pile. Repeat this step until one input pile is empty, at which time you can just take the remaining input pile and flip over the entire pile, placing it face down on the output pile. Oh, so you take the remaining input pile, place it face down on the output pile, take that, split in half. Let's think about how long it takes to merge two sorted piles of cards. Each basic step takes constant time. Since you are comparing just the two top cards, if the two sorted piles that you start with each have n divided by 2 cards, then the number of basic steps is at least n divided by 2. Since in whichever pile was emptied, every card was found to be smaller than the other card in the other pile. And at most n, actually at most n minus 1, since after n minus 1 basic steps, one of the piles must be empty. With each basic step taking constant time and the total number of basic steps between n divided by 2 and n, we can say that the merging time takes roughly proportional to n. That is, merging takes theta of n time. In detail, the merge procedure works as follows. It copies the two subarrays A, P through Q, and A, Q plus 1 through R into temporary arrays L and R left and right, and then merges the values of left and right back into A, P through R. Lines 1 and 2 compute lengths N and L, or N sub L and N sub R, of subarrays A, PQ, and AQ plus 1 through R respectively. Okay, so this is our merge sort algorithm here. Then line 3 creates arrays of L, so the 0 up through the Q plus the right, which is 0 through the for loops of the lines 4 through 5 copies the subarray of A, P through Q into L, and the for loop of lines 6 through 7 copies a subarray of A, Q plus 1 of R into R. Lines 8 through 18 illustrate in figure 2.3 perform the basic steps. The while loop of lines 12 through 18 repeatedly identifies the smallest value of the L and R that has yet to be copied back into the array. As the comments indicate, the index k gives the position of A that is being filled in, and the indices I and j give the positions in L and R respectively of the smallest remaining values. Eventually, either all of L or all of R is copied back into A, P through R, and this loop terminates. If the loop terminates because all of R has been copied back, that is because j equals to n sub R, then I is still less than n sub L, so that sum of L has yet to be copied back, and these values are the greatest in both L and R. In this case, the while loop of lines 20 through 23 copies the remaining values of the left array into the last few positions of A, P, Q through R, because j equals to n sub R. The while loop, okay, so this is just going over the merge sort here. How's it going over, dude? So I'm also going to take this image here. That one here as well. To see that the merge procedure runs in theta of n time, where n is equal to r minus p plus 1, observe that each of the lines 1 through 3 and 8 through 10 takes constant time, and the for loops in lines 4 through 7 takes theta nl plus nr equals to theta n time. To account for the 3 while loops, observe that each iteration of these loops copies exactly one value from L or R back into the array, and that every value is copied back into A exactly once. Therefore, the 3 loops together take a total of n iterations. Since each iteration of each of the 3 loops takes constant time, the total time spent in these 3 loops is theta of n. We can now use the merge procedure as a subroutine in the merge sort algorithm. The procedure merge sort, A, P, and R, on the facing page sorts the elements in the subarray. If P equals to R, the subarray has just one element and therefore is already sorted. Otherwise, we must have P be less than R, and merge sort runs the divide and conquer and combine steps. The divide step simply computes an index Q that partitions A, P, R into 2 adjacent subarrays, A, P, Q containing half of the elements, and A, Q plus 1 through R containing the other half, the right half. The initial call merge sort on the array of 1 through n sorts the entire array of 1 through n. Figure 2.4 illustrates the operation of the procedure for n equals 8, showing also the sequence of divide and merge steps. The algorithm recursively divides the array down to 1 element subarrays. The combined step merge pairs of 1 element subarrays to form sorted subarrays of length 2, merges those to form sorted subarrays of length 4, and merges those to form sorted subarrays of length 8. If n is not an exact power of 2, then some divide step creates subarrays whose lengths differ by 1. For example, when dividing a subarray into length 7, one subarray has a length of 4 and one has a length of 3. Regardless of the length of the 2 subarrays being merged, the time of the total merge of n items is theta of n. Got you. Copy that image too. Okay, we're almost there, everybody. Almost there. Stay with me here. Analyzing divide and conquer algorithms. When an algorithm contains a recursive call, you can often describe its running time as a recurrence equation or recurrence, which describes the overall running time of a problem of size n in terms of running time of the same algorithm on smaller inputs. Gotcha. You can then use mathematical tools to solve the recurrence and provide bounds on the performance of the algorithm. A recurrence for the running time of a divide and conquer algorithm falls out from the three steps of the basic method. As we did for the insertion sort, let T of n be the worst case running time of a problem of size n. If the problem size is small enough, let's say n is less than n sub 0, for some constant n sub 0 is greater than 0, the straightforward solution takes constant time, which we would write as theta of 1. Suppose that the subdivision of the problem yields a subproblems, which we would write with size n divided by b. That is, 1 divided by b is the size of the original problem. For merge sort, both a and b are 2, but you will see other divide and conquer algorithms in which a does not equal b. It takes t to the n divided by b time to solve one subproblem of size n divided by b. So it takes a times t to the n divided by b time to solve all a of them. If it takes d of n time to divide the problem into subproblems and c of n time to combine the solutions to subproblems and the solution to the original problem, we get the recurrence we get the recurrence. Chapter 4 shows how to solve common recurrences of this form. Oh, we get this recurrence. Sometimes the n divided by b size of the divide step isn't an integer. For example, the merge sort procedure divides the problem of size n into subproblems of size n divided by 2 and n divided by 2. Since the difference between n divided by 2 and n divided by 2 is at most 1, for which large n is much smaller than the effect of dividing n by 2, we'll squint a little and just call them both size n divided by 2. As Chapter 4 will discuss, the simplification of ignoring floors and ceilings does not generally affect the order of a growth solution to a divide and conquer recurrence. Another convention we'll adopt is to omit a statement of the base cases of the recurrence, which we'll also discuss in more detail in Chapter 4. The reason is that the base case are pretty much always t of n equals to theta of 1 if n is less than n naught, for some constant n naught is greater than 0. That's because the running time of an algorithm for an input of constant size is constant. We save ourselves a lot of extra writing by adopting this convention. Analysis of merge sort here. Here's how you set up the recurrence for t of n, the worst case running time of merge sort on n numbers. The divide step just computes the middle of the subarray, which takes the constant time. Recursively solving the two subproblems takes each size of n divided by 2, which contributes to 2t n divided by 2. Since the merge procedure on n elements subarray takes theta of n time, we have theta of n. When we add the functions dn and cn for the merge sort analysis, we are adding a function that is theta of n and a function that is theta of 1. This sum is a linear function of n, that is roughly proportional to n and n is large. So merge sorts dividing and combining algorithm times together are theta of n. Adding theta of n to the 2t n divided by 2 term for the conquer step gives the recurrence for the worst case running time of the merge sort as this. Pardon me. Chapter 4 presents the map. Jeez Louise. Oh boy. Got a frog in my throat. Been reading for an hour straight. Hour and 40 minutes. Chapter 4 presents the master theorem, which shows that T of n is equal to theta n log n, compared with insertion sort, whose worst case running time is theta n squared. Merge sort trades away a factor of n for a factor of log n because the logarithm function grows more slowly than any linear function. That's a good trade. Right? For large enough inputs, merge sort with its theta n log n worst case running time outperforms insertion sort's worst case running time, which is theta of n squared. So it's just showing you that in chapter 4, that T of n, which is this function, which is this merge sort growth rate, right, is the same as n log n, because it's n divided by 2 as we do is, and so it's just showing that that's a better algorithm, basically. It's kind of just giving you that preface. We do not need the master theorem, however, to understand intuitively why the solution to recurrence 2.3 is Tn of theta n log n. For simplicity, let's assume that n is exactly a power of 2, and that the implicit base case is n equals 1. The recurrence 2.3 is essentially theta, T of n, right? It is some constant I if n is equal to 1, or 2 times t, or 2t of n divided by 2 plus c2 times n. Where the constant c1 is greater than 0 represents the time required to solve a problem of one size, and the constant c2 is greater than 0 is the time per array element of the divide and combine steps. Figure 2.5 illustrates one way of figuring out the solution to recurrence 2.4. Part A shows the figure of the figure shows T of n, which part B expands into an equivalent tree representing the recurrence. The C2n term denotes the cost of dividing and combining the top level of recursion, and the two subtrees of the root are the two smaller recurrences T of n divided by 2. Part C shows this process carried one step further by expanding Tn divided by 2. The cost for dividing and combining at each of the two nodes at the second level of the recurrence is C sub 2 times n divided by 2. Continue to expand each node in the tree by breaking it into subsequent constituent parts as determined by the recurrence until the problem size gets down to 1 for each with a cost of C1. Part D shows the resulting recursion tree. Next, add the cost across each level of the tree. The top level has a cost of C2 times n. The next level has a total cost of C2 n divided by 2 plus C2 n divided by 2, which equals to C2 times n. The level after that has C2 n divided by 4, which equals C2 n divided by 4, which equals to C2 times n, and so on. Each level has twice as many nodes as the level above, but each node contributes only half the cost of a node from the level above. For one level to the next, doubling and halving cancel each other out, so that cost across each level is the same as C2 times n. In general, the level that is I levels below the top has 2 to the power of I nodes, each contributing a cost of some constant at that step times n divided by 2 to the power of I, so that the ith level below the top has a total cost of 2 to the power of I times C2 times n divided by 2 to the power of I, which equals to, what do you know, C2 times n. The bottom level has n nodes, each contributing a cost of C1 for a total cost of C1 times n. The total number of levels of the recursion tree in figure 2.5 is log n plus 1, where n is the number of leaves corresponding to the input size. And informal inductive argument justifies this claim. The base case occurs when n equals 1, in which case the tree only has one level. Since log 1 is equal to 0, we have that log n plus 1 gives the correct number of levels. Assume, as an inductive hypothesis, that the number of levels of a recursion tree with 2 to the power of I leaves gives the log 2 to the power of I plus 1 equals to I plus 1. Since for any value of I, we have that log 2 to the power of I equals to I. Because we assume that the input size is an exact power of 2, the next input size to consider is 2 to the power of I plus 1. A tree with n equals to 2 of I plus 1 leaves has one more level with a tree than 2 to the power of I leaves. And so that total number, to compute the total cost represented by the recurrence, 2.4, simply add up the cost of all the levels. The recursion tree has log n plus 1 levels. The levels above the leaves each cost C2 plus n times n, and the leaf levels cost C1 times n, for a total cost of C2 n log n plus C1 log times n, which equals theta n log n. And we got some exercises here. And I think that is almost there. So then we have some practice problems here, exercises that we'll do at a different time. Then we have problems. Oh, cool. That's the end of the chapter. Oh, cool. All right. Holy crap, that was a lot. That's going to take me a while to edit down. All right, you guys. Thanks so much for, I'm going to go ahead and stop the recording here, so I'm just going to do a little sign off. All right, thanks so much for watching this video on the channel. Hope you enjoyed Chapter 2 of Introduction to Algorithms, 4th edition here. This was awesome. I appreciate you guys being here and joining me for this one. This was a good review over some algorithm time and growth rates. Getting into asymptotic notation in the next chapter will help solidify these and this review. All right. All right, my name is Michael. I'll see you guys in the next one. Thank you. All right, I stopped the recording there. Cool. So I'm going to go ahead and chop back up the, I'm not done yet, you guys. Hold up. I'll go back through and chop up the recording. That was just for the recording. I'll go back through and chop that up. I'll get rid of all the repeats and the blank pauses and the just make it so it's kind of like a fluid audiobook, just like an hour straight of reading the whole chapter, so that if you would like to go back through and read the chapter on your own, but kind of read it with me again, you can do so. It's kind of a great, I think it's a really cool tool. There's not a lot of resources I found out there that kind of have these books in kind of like an audio style, work alongside peer-to-peer format. I haven't seen anyone really do this, because a lot of people just don't want to work through these books in general. I don't know why people just don't like textbooks nowadays. It's honestly if you want to learn college without actually paying for college, just pick up one of these PDFs for real. Honestly, in my college chemistry courses and stuff, if I didn't really understand stuff, I just read out of the book, and taught myself that way. So these textbooks, you guys, are the hacks to college. A lot of people really have the negative connotation and view behind textbooks has um, grown substantially over the years. But if you guys are wanting to do well in your classes, a lot of the times, if you just read the book before you go to lecture and go into lecture like with some, you know, 50%, 60% understanding of what you're talking about that day, you solidify that up to like 80, 90%. Then you do like a little bit of review like outside of class, and then you do a little bit of like review before the test. You'll be, it's golden. Like it's about that process. Like if you kind of take it in chunks over the course of time rather than just mass like mass entries of data right before like cram sessions. Like it's not, you know. Hey bro, I want to start the algorithms. Let me know when it's up on Discord. Yeah, so let me go ahead and put it up right now. So this is my Discord. You guys can access it in my description below. I've got my, it's kind of like an entire roadmap of my learning journey so far. Wait. Wait, you guys. Did that not record? My screen's frozen. Did my screen just freeze just now? Or has it been frozen this whole time? Oh my god. I swear to god, dude. That was a really good one. Oh crap. So it just looks like the last 20 minutes, for some reason, something happened with my stream. Okay, it's not terrible. It's only the last 20 minutes. Oh, that's kind of, that sucks. Why has it been broken? What the heck happened? That sucks. So we got stopped at. Was when I went over to ask ChatGPT for some help. Shoot. That sucks. Really bad. That actually is so tragic. It's all right. I'll just make a little note. Like it was only the last 20 minutes of the 2 hour reading, so it really was just the last like couple of pages, right? It's not like, well, what I might have to do is I might have to go back and read it off stream and then add it to the video, which it's fine. Whatever. It is what it is. Okay, I also need to go back through. I'm gonna go back through as well when I edit my video and put in like the definitions and stuff and fill in my notes as well. I just didn't want to like do a bunch of like note taking as while I was reading as because it just would take like 3 or 4 hours to get through this chapter, right? Rather than the two it took right now. So we fell off where? We fell off at when we were getting into theta. The Greek letter theta, yeah, when it was teaching us about theta, which is all the way back here. So designing algorithms basically in forward. So like, mm, all right. I am done for tonight though, you guys. I read for 2 hours out loud. Anyways, we finished chapter 2. I'll go back. We'll go back through and complete these problems and stuff before we move on to chapter 3. I've got quite a bit I need to do. We need to finish the next problem set of MIT 60002. We need to build our project. We need to continue reading this book. Man, I'm not in school, but let me tell you, dude, I feel like I'm back in school. I feel like I've got a schedule. I feel like I've got tests. I feel like I'm like stressing out over self-inflicted assignments. Like I feel like I have a professor that's like grilling down my back, but it's just you guys. Oh my gosh, I'm trolling myself. I'm just like self-inflicted pain here. For what? Anyways, you guys, I appreciate you being here. My name is Michael. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist 9 to 5 every single day, Monday through Friday. And I teach myself how to code afterwards at around 7 p.m. PST every single day. I appreciate you guys can. Oh, that's right. Sorry, I forgot. Let's go and fix this. Okay, so let's take. Let me go here. Let me delete the old ones. Rename Corman Introduction to Al for edition. Okay, and then we go here. Remove that attachment. Exceeds the limit. No. Okay, what I'll have to do is I'm going to go to Google Drive. I'll sign in to my Google Drive on my Google account. Yes. Home. My Drive. Let me upload the book to here. Where'd it go? Okay, there it is. Let's go here. Share. Share. Anyone with link? Okay, copy that. I'll say, we'll do, here is a, I'll say I have uploaded the PDF. To my Google as a due to size. And then we'll do a link here. We'll do Corman intro. We'll go in. We'll copy this and paste the link. Say 4th. All right. Let me know if that works, Carlos. Hey, Ray, I appreciate you coming in every day, dude. Are you in the Discord, Ray? I might need to mod you up, my guy. You come in here every day. We might have to, Mahan, he might need to get the boot from mod status. He never comes in anymore. He'll probably come in when his school starts again, but until then, he might need to get demodded. We might need to bump Ray and bump Carlos up to come in every day. Let me know if that link works. Let me rename the file to the same one that we have here, just so it's a consistent. Introduction to Algorithms, CLRS. We'll say 4th edition. Let me know if that works. Awesome, Ray. Just uploaded the 4th edition of the I was using the 2nd. Shout out Tim Player. let's copy. Nothing yet? Nothing yet. Hold on. Let me see if the channel is being hidden by default. Hold on. Server settings. No, it's the first thing, right? It's server settings, onboarding, default channels. It's hidden. Why does it do this? Sorry, I had to set it as a default channel. All right, you should be good now, Carlos. You should see actually the MIT OpenCourseWare channel that I had here was actually hidden. So, which I need to go back through and start uploading. Dude, I'm so behind. Oh my God. I need to do weekly breakdowns up to like week 8 so far, or like week 6 of MIT 60002. Can we do a period? No. So I like I did for the Harvard CS50, I need to go back through and do weekly breakdowns, and I need to finish this. I need to post my final project on here. I still have CS50X videos I need to upload, like the last couple of videos. Oh my God. Okay, this weekend, this freaking weekend, we are getting caught up on the videos. We are going to get caught up on, I'm going to post all of the CS50X videos that we have already done. We've already completed the course. I just need to post the watch-alongs from the stream. I need to cut them up and post them. I have them recorded and downloaded already. I need to make an entry for my final project onto here. I need to make entries for Harvard CS50P. I have to backdate entries. I need to make entries for MIT. Oh my gosh. This is turning into a full-time job. I'm double employed. A late train won't miss the station. Nice, good hard work, good wise words. Carlos, did you finish Python Crash Course? 1 hour technical interview with the VP of engineering and a senior software engineer coming up, and I'm stressed out. Bro, you must have like the ATS resume do a T. You got like you are probably the most frequent interviewer I've ever come across. Now, don't take that. Please don't take that as a dig in terms of that you're constantly interviewing. Oh God. I promise you, you will stop interviewing one of these days. You're gonna get one of these. The interviews will stop, but keep going. Keep doing interviews. But I don't know. It's kind of funny. It's a double-edged sword. Double-edged sword. But honestly, though, like in terms of like quantity, I've never come across someone that's interviewed as much though. So like the fact that you're getting these opportunities is pretty nice. All right. Keep getting ghosted. Oh, brutal, man. I gotta finish the first project. Oh God, I didn't finish the I'm just talking about the part one. Did you finish part one, Carlos? I didn't do any of part two. I didn't make any of the projects because I was kind of already like building kind of my own, I guess, and it's kind of like a way to like if you don't have any like experience like starting from a blank terminal maybe or like coming up with ideas, it kind of helps to. That was my I have this Fidelity account I get like alerts from. I have just like $25 sitting in this Fidelity account that I get alerts from like every night about for some reason. I've got to figure that out. It didn't pop up anything sensitive. I don't think so. Yeah. Okay, good. Phew. Just said 27. Yeah. I have $27 sitting in this Fidelity account that I just have by default because I want to open up my retirements and stuff. And I get like a text about it every night. Nice, Carlos. All the part one. That's good. That's the meat of it. That's all the info right there. Are you? Yeah. Start. I definitely. You should definitely start this book, and then also, I found I've been starting to read my Fluent Python book again, and I have found that it's actually kind of pairing well with this book in terms of like um the just like being obviously just being better at syntax is helping with like understanding these algorithm stuff, being better with understanding index slicing and like being better with loops and just like more fluent Python as the book name says, like it's just helping to increase my bandwidth for understanding. And the only problem these days is AI interviews are impossible to crack because they capture half the stuff wrong and the other way around. It's getting tougher and tougher. Dang. All right, you guys. Thank you guys so much for joining me here on August 28th, 2025. We read chapter 2 of our introduction to. Wait, why is my. Why is that? Why is my thing frozen again? Why does it keep freezing? Yeah, please let me know if the screen freezes. Like if like I for some reason it's like let me see if I like hit my desk, will it freeze? Sorry, hold on. Pardon your ears. No. Like I'm trying to like jiggle the dock cord or something. Hmm. If I click off, come back. No. If I go to ChatGPT and come back. No. Something's yeah, weird. Yeah, some I don't know why my it keeps getting stuck on my like display capture input keeps getting stuck on I don't know if I'm bumping my cord or something, but yeah, it's being weird. It's absurd how many companies have asked me why I switched to NeoVim when I can use Cursor. So that they explicitly are asking you like in term in like a condescending way, like why are you using a blank IDE when you could just use AI? I don't know, dude. I really think it might there might we can theory and brainstorm all we want. It might go too far. Like it might go to the point where it goes too far too fast down one avenue, and there's too much change too quickly, and human nature just resists. Like I can see it just getting kind of like dumb, right? Like questions like that like are just getting kind of like dumb. Like, oh, you want me to just not use a IDE just because there's AI, like, or a text editor, like, so you want me to what? Just not program? Like, I don't know. I feel like it's gonna go. It might just be. It might get pushed so far to one end of the spectrum that you just get such a rapid, a drastic rebound against maybe that like to combat. Like you might just get people that like, honestly, people just might come together and like refuse to do like these leak code interviews, to do these. But dude, honestly, it's just so competitive, and there's so many people that it really you won't get everyone on board. But in order, honestly, in order for things to change, that's what you're gonna have to do. Is you're gonna have people get job interviews, get like OA assessments, and refuse to take them. Like they're gonna have to say like no, like I'm sorry, like I have experience, I have a degree, I have projects. Like I'm not gonna take waste my time on your OA. I'm not gonna waste my time on your take home assessment. I'm not gonna come in for a 2 hour coding screen. Like you have all this pre existing stuff. You have AI now. Like there's no like you said, there's AI now. There's no point for me to be doing these assessments in front of you. Like it just seems so silly. It seems so convoluted. Like, oh, we have AI now. Why even code? But let's judge you by an OA. What? What do you guys think about that? Anybody have any opinions? Well, I'll wait for you guys' chat, and I'll just and then we'll call it here at 2.5. We'll wait 2 minutes, and we'll call it at 2.5. Yeah. AI coding sucks. AI assisted coding rocks. Honestly, though, in some instances of like AI assisted coding, I feel like guilty sometimes though. The only people benefiting are those who can architect systems and understand how to scale them. All you're saying is true, Carlos says. People are agreeing. It's really just like this rock and a hard place. Like you just unfortunately like you have to have power in numbers, and people are so desperate for work and money like that you will just never you're not going to get a unionization of programmers to like combat this job market. Like it's just I really think that those days are over. People have the mindset of kind of like honestly every man for himself. That's the large majority of the mindset. And like it's cutthroat. It's like it's dog eat dog, right? Yeah, and it's really like honestly, I'm just kind of getting like honestly like annoyed of the conversation. Like it's just being talked about so much, and like being brought up like everyone's being is concerned about it, which is totally valid. Like it's so valid to have these concerns, but it's just getting like annoying though, like in terms of the grand the overall umbrella of it. Like, and I think it's becoming annoying because it's impacting us. Like that's why it's maybe annoying, right? It's because like, oh, we're hearing these same stories over and over again, and it's just not getting any better though. Like everybody's just saying like, oh, let's just wait it out. Like let's just stick in there, just hang in there. I mean, we've been waiting since like 2023, the beginning of 2024, end of 2023. Like we've been waiting like 2 years now, a year and 3 quarters, like 2 years. Like you're gonna wait and make people wait like 3 4 years for a job market turnaround. Like that's hundreds of thousands of dollars in wages lost. That's like a retire. That's million hundreds of thousands of dollars of compounded returns lost in a retirement 401k with the company match. Like I just really, I don't know, dude. Like I honestly, I try to be, I just think the best way I try to combat it is just ignorance. Like just ignore and just try to just code. And I have a job, so I'm blessed in that standpoint. And like I can, but in complete transparency, I have applied to biotech companies, entry scientist positions, manufacturing scientists, reagent manufacturing, control manufacturing, uh, drug synthesization, drug discovery, research and development, quality control, QA, quality assurance. I've applied to, you know, I get nothing, and I have a pretty nice resume. I work at a Fortune 500 that I contribute personally millions of dollars of actual revenue to, for the products I develop and innovate for them. And so like, dude, I just don't know. Like I really am trying not to just complain and whine because I feel like that's also the bad mentality to have. And it's just, but it's so easy to, right? It's just, I wrote a blog a few years ago, quote, have we forgotten how to code? And that was before AI. And most common questions I got asked in the past interviews is how do you leverage AI in your workflow? Carlos says the same stories over and over and over again. What do you do for work? I work as a formulation chemist for a biotech company. I have a degree in human biology and a minor in chemistry, and I got a job just at the very end of the hiring frenzy in tech and biotech at the end of 2021, beginning of 2022. I got really lucky that I graduated right then at the very end. I wish I graduated like a semester sooner. It would have been even easier. But as soon as I got my job, literally like 6 months later, hiring just shut down across everything in tech, biotech area. Like it just, like it was really kind of crazy how fast it shut down. And so people started clinging to jobs desperately. Like and like I got really lucky with the timing of it. And so like, I've just been kind of a sitting duck, you guys. Like I've just been waiting for opportunities to come around. I've been practicing my skills, just kind of like an NBA player waiting for his free agency, someone to call him out of free agency. I kind of get why AI becomes this rampant. It's because there's just so much stuff a software engineer job requires from a candidate. It's impossible for them to keep up by raw dogging it all. Yeah. I don't know. It's just everybody's got opinions, everybody's got ideas, and there's just no solutions. And so it really just feels like this empty void that everybody's just spitballing into, just shooting spitballs at, and just hoping that something hits a target when it's just getting, you have a fan blowing your spitballs into the trash, as they're trying to get there. Like it really, that's honestly is what it feels like. It's just this feeling of just helplessness. I don't know, dude. Are you guys feeling that too? Like, for those, honestly, like be real with me, guys. Like, if for those that are unemployed, like, how is the morale? Like, I couldn't even imagine like trying to struggle to pay some bills under some of these circumstances, right? Like, it just, you know, it's just so nuts, so nuts, man. Yeah, no, and then though, I feel like candidates and CS majors, they put all that stuff on their resume, and it's kind of like a lie though. Like in all honesty, I feel like the large majority of the CS majors and people, they're taught these core level computer hardware architectures, so, design and or whatever, classes and whatnot, mathematics and general eds and stuff. And a lot of them don't have deep level understandings of React, Next, Fast API, Django, Express, SQL, NoSQL, all of those, right? But a lot of them list it on their resume, so I feel like there is like this kind of facade or like disconnect or like lie that's kind of like been presented like, oh, I need to know all these, but I actually only know like how to write like 10 lines of code in, or do like a single select query in the SQLite or whatever, like a select star, like that. but I don't know, like, so that's why my approach with Python and with like the books and stuff is I'm really trying to just grind multiple libraries in Python, like really gain an overarching umbrella understanding of the entire platform of Python before moving on to other languages. Whereas my coding skills and understandings of the concepts are really solid to a core level, and then I can apply those to other things. But I'm really not sure like that these CS majors know all of those things. I feel like it's just kind of like they're just throwing out these key highlight words to just get past the ATS screenings and whatnot. We've stepped into the twilight zone. Yeah, we were going way over here, Ray. This also led to an inflation in salaries as well. Like if we're hiring three people for three roles of Edgewise instead of now hiring one person that can move fast for a little under X. Yeah, I also thought about that too. Like but there's also some underlying costs, Anon, that you have to think about of like not only the salary, but they all like the retirement match, the benefit package, the comp, the money that the company has to invest not only in salary but in those other fields. I feel like that's what deters companies from lowering the salaries and then increasing the headcount. Like, what if you just lowered tech salaries from the average of 160 or whatever, one not even that, maybe Bay Area 160, right? Bay Area like 140. Like, if you lowered it to like 110, right, and then just doubled the role, but it's just I don't think the budget's there. I think it's already like in like a business sense, in a business case, like it really kind of only makes sense to have like one master skill catch-all guy. I don't know, dude. It sucks. It just sucks. It just sucks. Anyways, I'm done talking about it. I'm done thinking about it. I'm gonna go turn off my brain and watch some Silicon Valley and just be done. Anyways, you guys, I'll be back tomorrow. We will continue on. Um, I want to. I'm wanting to keep. I'm trying to my best to balance the studying of like the books and note taking with my project work because I want to keep up in all areas. I want to keep building projects to gain actual feasible experience building real world tools, but also developing my skills intellectually by diving deeper into more core level fundamentals of programming and computer science. So, but I'm also just struggling to balance that all under the 3 or so hours I have after work. But I appreciate you guys being here. Hey, bro, you turning into your videos is wondering how long it took you to master the fundamentals like syntax. Um, yeah, it really started to ramp up as I started going every single day. It really helps to understand those small syntactual things and nuances if you're familiarizing yourself with it on a daily basis. If you allow time in between sessions and study sessions, like upwards of like 3, 4, 5 to a week, 2 weeks, you'll just regress. You really have to compound those syntax, those little things every single day, or every other day, or every 2 days, like really like frequently on a frequent basis to just kind of it's just like practice makes perfect, man. It's pretty cliche and it's pretty cringe, but it's honestly very true. You're not going to get better at the guitar unless you pull it out of the case and start strumming. So thank you guys so much for being here, and I'll see you guys tomorrow. My name's Michael. Thanks so much for being here, and please subscribe and like the stream. If you guys are here and haven't liked, please do so. It really, really helps to get new people in here. It's free. I sit in front of my camera for over 2, 3, 4 hours sometimes for free, providing you guys content here. So in the Discord, lots of time. So just if you guys could leave a like and sub, it's really helpful. So thank you guys so much. See you guys tomorrow. One thing I realized when coding almost feels like you have to unlock your creativity versus being sad. Yeah, exactly. It's a very creative field. That's why sometimes computer science and programming is considered a Bachelor of Art rather than a Bachelor of Science at some institutions, because there is a very creative aspect of programming. Anyways, sorry guys. See you guys. Have a good